So this is week 2 online live session, uh, which is on urban utilities planning, water supply, sanitation and drainage. The course instructor is Dr. Devapratim Pandit. He is a professor in Department of Architecture and Regional Planning at IIT Kharagpur. I am the teaching assistant of this course. I am Vaibhav Kabadwal. I am a research scholar in environmental engineering discipline in the Department of Civil Engineering at IIT Madras. So we will start with the week 2 session. So let's solve one problem related to the population forecasting. We learned population forecasting in the previous online in the previous session. So here is a question. So the question says the present population is 56,000 and the water demand is 8400 meter cube per day, and it is expected that population after 20 years will be 88,000. The treatment plant capacity is 12,000 meter cube per day, and it is asked that after how many years from now the plant will reach its design capacity, and we have to assume geometric increase method, which means geometric growth of rate method. I hope I am audible and you can see my screen. You can text. So we will solve this question. So it has been given. We are provided with P naught. Is 56,000. After 20 years, I am writing it as P20. It is 88,000. And let's write it like this. So at P0, the water demand is 8400 meter cube per day. 8400 meter cube per day. And we need to find the capacity is, the treatment plant capacity is 12,000 meter cube per day. 12,000 meter cube per day. Capacity is 12,000 meter cube per day. So we will find out where first, like, that 12,000 meter cube will reach within 20 years or after 20 years. So let's calculate that first. So I will first calculate. So for this much population, 84,000 meter cube per day, water is required. So we will calculate for per person how much is the requirement. So water demand, we'll find out water demand in liter per capita per day. That will be 8400 into, I'm converting it into the liters, so it will be liter liters per day. I'm dividing it by the population, which is 56,000. So how much we will get? We calculate 8,400 into 1000 divided by 56,000, that is 150 LPCT, liter per capita per day, or it can be written as LPHD, is liter per head per day. So for P20, let's find it out. Let's not find out for P20. Let's calculate how for 12,000. For this, when it is reached 12,000, so how much population is there at that time? Population served by the treatment plant capacity. Full capacity. How to calculate? We will divide this 12,000 meter cube per day by 150 meter cube per day by population, by water required by per person. Water required per capita. So now we can write it like into 1000 liters per day So how much is the population? Let's calculate it. The population comes out to be 80,000. 80,000. So so the population comes out to be 80,000 here. So it will reach the capacity before 20 years. So before 20 years, it will reach its capacity. So its capacity will be 12,000 meter cube per day. If the capacity would have been more than this value or whatever is required here, then we need to calculate after 2 decades. But the capacity is less, so it will reach before 20 years. So now we need to find it out how much. So when population will grow till 80,000. So now we will calculate it with the help of geometric increase method. So we know geometric increase method, Pn is equals to P naught 1 plus R to the power n. So first we need to calculate R. We know at P20, we know P0, but we don't know R, we know N is 2. So we will calculate it like under root P20 divided by P naught minus 1 is equals to R. If we will solve it, how much we will get? PR is P20 is 88 by 56. Indirectly write it as 88 88,000 by 56,000 minus 1. We are getting R as 0.253, or we can say percentage R will be 25.3%. And from here we can use R to calculate PT. At what time the population of 8,000, at what time this population will reach 80,000. Now we can calculate, write it as PT is equals to P naught 1 plus R to the power n. This time we need to calculate n. We know PT is 80,000, P naught is 56,000, R is, we can combinedly write it as 1 plus 0.253 to the power n. So 80 divided by 56 is equals to 1.253 to the power n. Let's take log on both sides. Log 80 divided by 56 is equals to n log 1.253. So here we can calculate n as, let me calculate, log 0.1549 divided by log 1.253, 0.970 979. Now calculate this. 1549 0.0979, 1.58, n is equals to 1.58. So this is decade, n is decade. So from this we can comment that after how much, after how many years, after 15.8 years, the plant will reach its design capacity. After 15.8 years. So this is the answer of this question. Now we can proceed with few MCQs. So what are the key issues related to water? These are the general points which we see which we see every day related to the water. You can think about these general key issues. These are fresh water availability. So let me just write it down. So as we know, quality, quantity, these are the issues. And apart from that, quality is deteriorating day by day, quantity is getting reduced because of the wastewater we are producing. We are producing wastewater out of fresh water, and the population is increasing and the glaciers are melting. Because of that, flooding, rock avalanches, in snow when it falls with soil and rock. These are rock avalanches. These are affecting the water resources. So quality is deteriorating, quantity is also getting reduced, and uh, the because of the melting of the glaciers and all, we are affected, and lifestyle change. Because of the lifestyle change, we are producing more water and wastewater, more wastewater actually. And population growth itself is a big issue. So these are the key issues related to the water. Why there is a need to forecast the water demand? So why do we need to forecast the water demand? So the need is because future consumption. We are studying this course because we want to we want urban utilities like water treatment plant, wastewater treatment plant. So wastewater treatment plant are designed for at least 30 years, at least 20 years, let's say. So for that, we need water demand for future. So that's why we want to estimate future water consumption. And what are the factors which affect the dynamics of water usage? The dynamics here defines like how water is getting, like what is the water available, what is the population, what are the cultural differences, and what is the attitude of people towards water. So these are the dynamics of water usage. And design and operation of water supply infrastructure. Like initially I told, we need to design the water supply infrastructure like water treatment plant. After that, we need to design the service reservoir. So let's take the example. So after water treatment plant, it will be sent to a service reservoir. Let's take this is overhead tank. This is overhead tank, and from this overhead tank, it should be designed to distribution system. So this is distribution system. So we need to know what is the demand here. We need to know what is the demand here. We need to know the demand this side, then only we can design these two things. So because of this, we need to have water demand, and the state has the responsibility to provide the water. So because of pricing also, how much price, at what price the water should be the water should be sold. So we need to have the idea of water demand and accurate estimate of peak water demand. So we also need peak water demand, because sometimes in summers what happens, we uh, we want peak flow, because the we'll study about this maximum hourly flow in fluctuations. We'll study it later. So we need these pipelines in water distribution. These are designed for maximum hourly flow. So when there is a fire or something, uh, we need to take care of peak water demand also and fire demand also. So that's why we need to know water demand. How much water liter per head per day to be supplied through stand post as per IS 1172/1993 to the communities with population up to 20,000. So through stand posts are actually these are provided in the locality of where less population is there. It's not for urban, it is mostly suburban or rural areas where a tap is provided for the uh, for let's say the community of around uh, 5, 7 homes or 10 homes at least. So in a street, you can assume like two taps are provided. So these are called stand post. So the water provided, water supplied through stand post as per IS 117/1993 is 40 liter per hour per day. So through stand post, it is provided as 40 liter per hour per day. So this is the minimum water that we need to take care. So the minimum water. It can be more also. And we can see some other examples here. So water supply through house connections. So house connections means the connections are provided in house. Means inside the house you will have a water connection. So this will be 70 to 100 liter per capita per day or liter per head per day. And for communities 20,000 to, so this will be 1 lakh. 20,000 to 1 lakh with full flushing system is 100 to 135. And for the communities for with population more than 1 lakh, the water supplied should be 150 to 200 liter per day. For economic weaker section and low income group colonies, it is 135 liter per head per day. This is as per National Building Code 2016. So, what is the total water demand? Means what does it include? So it includes domestic water demand, industrial water demand, institutional and commercial water demand, demand for public uses, losses and waste, and fire demand. So these are all the demands which are taken into account for a water supply scheme or for the water supply infrastructure. So we'll talk about all those demands one by one. One by one we listed. So what is domestic water demand? You can think a domestic in our households in the residential building, what is the total demand of water for cooking food, for bathing, for let's take the example. So for drinking we need water, for cooking we need water, for bathing, for washing clothes, utensils, washing and cleaning houses and residences, lawn watering and gardening, flushing of water and closets, flushing of water closets. This is the toilet flushing. Yeah, I did mention it here. So full flushing system means water closets means your commode and all they have flushing system. So flushing system will require more water demand. So this means flushing system. So if we add all those things, we will get 200 liter per capita per day. So per person is 200 liter per capita per day. And for low income group colonies, so some things are like for flushing of water closets, it is less, and for bathing it is less, and for washing of clothes it is 5 liter less. So likewise it is less. So the domestic water demand includes water required in private buildings for drinking, cooking, bathing, lawn sprinkling, gardening, sanitary purpose, etc. So IS code specifies the domestic water consumption between 135 to 200 liter per capita per day. In developed countries, this is high, as 340 liter per capita per day. So the domestic water consumption is 50 to 60% of the total water consumption, total water demand. So this is as per this SD code. So now what is industrial water demand? Industrial water, industrial water demand includes automobile industry, where vehicles are manufactured or made. distillery where alcohol is made. So these all exert water demand. Fertilizer industry, paper industry, uh, steel industry, sugar, textile, dye, and all, they need water. So the per capita consumption for industrial demand of a city is 50 liters. For industrial, it is 50 liter LPCD. It is based on the population of a city. Population of a city. 50 liters per person per day. Small scattered industries are industries, but not for the larger industries, which has to be estimated separately. So this data is on an average, but for larger industries, it should be estimated separately. Institutional and commercial water demand. So what does it include? It includes like institutes and commercial activities like offices. They're apart from our residential buildings and industries. We have offices, factories, cinema halls, schools, colleges, hotels, restaurants, airport, international, domestic, whatever, railway stations and hospitals. So these will also require water. So the per capita demand is 20 liter per capita per day, usually considered. In highly commercialized cities, this can be taken as 50 liter per capita per day. What is the demand for public uses? So what is public use? How it can be, how how we can decide which is public use and which is personal use? The public use is defined as like we have roads. So for road cleaning, water is required. That is a public entity. So public parks and gardens. So the water required there for public fountains in the parks or somewhere else. So this is public use. And like in the public, we have public toilets. So for that, the water is required for cleaning and for flushing. So water is required for cleaning public sanitary facilities and maintaining hygiene standard in public restrooms. So this is the demand exerted by the public use. So in India, 5% of the total consumption is considered enough to meet this demand. So the 5% of total demand is considered enough. And it is usually considered as 10 liter per capita per day. 10 liter per capita per day. So for a city, we can consider it as, so if the city population is 1 lakh, so we will multiply it with 1 lakh. 10 liter per capita per day into 1 lakh. That's it. What is law? In water demand, we have losses and theft and waste. What is this? So this accounts for 15% of the total consumption. And this is due to bad plumbing because the pipes are not continuous entities. In pipes, if you have studied hydraulics or fluid mechanics, we have joints here. Pipes have joints. Pipes are connected with the help of joints. And in joints, there is always a leakage. We can make, but most of the time there is a leakage. So these are not leakage proof. So bad plumbing can cause loss of water and defective joints like I both are interrelated and damaged water meters. So what happens? Uh, the damaged water meters will not account for the water which is going in a household or which is being utilized by the group of people. So this will be considered as a loss and waste. What is fire demand? This is the last demand. What is fire demand? As the name suggests, so when fire broke out, we need to have some water. So that water demand that water requirement is called fire water demand. So the quantity of water required for firefighting, that should be kept stored in storage reservoir and made available always. Suppose this is the water tank here. You might have seen the overhead tanks like this at the outskirts or in the middle of the city. So this much water should be contained every time. Let's take this, we will calculate it also. So this much required at every time. So why? Because of this fire demand. Because of fire demand. The water. So after this, we are supplying the water to the distribution system. The water distribution system is affected by fire demand since consumption of water during firefighting is high. Minimum water pressure to be maintained for fire hydrants for fire demand. So how much is the minimum pressure we need to maintain for the fire hydrants? So what are fire hydrants? Fire hydrants are nothing. These are provided like stand posts. They are provided on the ground on the near the streets. To they have uh, like taps, but they are used when there is a fire. So these are red in color. You can check in Google also. So the minimum pressure to be maintained for fire hydrants. So the fire hydrants are the equipments which are used to extinguish the fire. Um, Using the if we connect those fire hydrants with pipe, we can with a hose. These are used to extinguish the fire. So the water pressure which is to be maintained is 10 to 15 meter of water head. So 10 to 15 meter of water head is required. So means if we consider 3 meter as one story building, so 15 divided by 3 means 5, means 5 floors, means it should have pressure to supply the water till 5th floor, so that the water if water can go up to the 5 floors, 5th floor, so it can extinguish the fire. It can extinguish the fire till 5th floor, not above that. So this much water pressure should be maintained, and this water pressure should be maintained even after 4 to 5 hours of the constant use of fire hydrant. Means the water here should be sufficient enough. In this tank, this is overhead tank. Either it should be at much higher, much larger height, or we need to have pumping system in the water hydrant. So why this much head is required? For adequate flow rate. So for extinguishing the fire, we should have adequate flow rate. For reaching the height and distance, so at a particular distance and height, it should reach, and overcoming the friction loss. So this does not mean like it can directly reach till the 5th floor. If there are friction loss in the pipe, yeah, pipe which are connected to the hydrant, so then it can have some loss and it may not reach into the 5th floor. It can reach up to the 4th floor only. So for overcoming the friction loss, we need to provide more pressure, more water pressure, and operational efficiency and fire equipment. So the firefighting equipment include hoses, nozzles, and pumps. These are designed to operate optimally at certain pressure level. So they require pressure. Ensuring a minimum pressure helps maintain the operational efficiency and effectiveness of this equipment. So if a minimum pressure is there, then only it can work effectively and efficiently. Now another question, factors which can affect per capita water demand. So factors are like climatic condition. This is the easiest one. The climatic condition. Let's say the consumption is more in hot and dry places, and also in very cold. In hot places, it is more. In cold areas, it is less. In cold areas, more leakage due to contraction of pipe, and people keep taps open to avoid freezing of water. So because of this, there are different water consumption in different climatic conditions. Standard of living. So if economic status is good, the people will use more water, maybe because of full flushing system and all. They will use bathtubs and all. So standard of living affects the per capita water demand. Industrial activities and commercial activities. So if you see the industrial area and if you see like more steel plants, sugarcane industry, distillery nearby your area, so the water demand of your area will increase. So if you this is not yeah, if you supply good quality water, the water demand uh, will be no, it should be understood like if the quality of water is not good, then the demand will decrease. Then people will buy water from other sources. They will try to find other sources. So if quality decreases, then people will go for another source. Pressure in distribution system. So more leakage, more consumption by the people in upper stories. So if the pressure is fine, understand it like this. Suppose the pressure is less. I need to make it right. So if the pressure is less, the water can't go till top floor. Here, water cannot go. Let's say water can go up to this level only. So to get water at this level, I need to provide pump. So what pump will do? Pump will exert extra energy, and more extra energy will cause more leakage, and this leakage will cause more consumption. This is the issue. If pressure is less, then people staying in the top stories will require pump, and this pump will cause more leakage, and more leakage will cause more demand. System of sanitation. So if full flushing system is used, then more consumption, more demand, and if not, less demand. System of supply. So intermittent and continuous. So there are so in intermittent system, the water is supplied at a particular time. So what happens? The people where the people who are using where the intermittent supply is there, people generally keep their taps open to know whether the water has come or not. And they first thing is that can cause loss of water, and secondly, in intermittent system, the people store water, and if the freshly arrived water comes, they tend to throw the water stored. And while in continuous system, there is a continuous supply of water, so there is more leakage. So this is the ideology of both system of supply, like in intermittent and in continuous systems. The cost of water and metering. So if we will provide metering and all, then we can put tariffs so that we can get the estimated amount of water. So the uncontrolled wastage can be avoided if we provide meters. So water demand in urban areas are estimated using. So which IS code is used? So water demand in urban areas is estimated using IS 1172 1993. So what is fluctuation in water demand? So uh, if you see, like let's take the example of Delhi. So the water demand in July, and if you see the water demand in December. So from month to month, the water demand will change because July is summer, December is winter. So the water demand will change month wise, and month wise it will also change. Weekly also it will change. Daily also it will change, and hourly also it will change. So this change is called fluctuation. This change is called fluctuation, and how this fluctuation is required is incorporated into the design, and why how it is useful. So we can say, like, suppose let's take a river. Suppose we require 8,000. Let's take the example of first question. What was that? For a community, how much was the demand? 8,400 meter cube per day. So 8,400 meter cube per day is the water demand. Suppose during the summers, the river water level will go down. River water level goes down in summer, we know, and it can't meet this much demand. So are we going to use this as a water source? So to identify the water source, we should know what is the fluctuation. So this is the per day, and if we want peak flow, we need to multiply it with 8. Suppose if this river can't meet our peak fluctuation, which mostly occurs in summer, so then we need to identify the source based on this fluctuation. For the pumping units, so at peak flow, let's say if there is fire demand or something, so we need to design the pumps based on the peak hourly flow. So the fluctuation is required, and pipes are also designed based on the flow rate. So if we require more water, we need to have more dia of the pipe. And design of service reservoir. So service reservoir is also designed based on the peak hourly flow. And it is also, the fluctuations are also helpful for the design of sewers and wastewater treatment plants. So at what rate we are consuming, mostly mostly at the same rate we are generating the sewage also, or wastewater from our households. So we need to design the sewers or sewerage system and wastewater treatment plant accordingly. So that's why the fluctuations are required, or that's why we try to find out the fluctuations in the water demand, daily, weekly, hourly, monthly, to design the uh, water treatment infrastructure, wastewater treatment infrastructure, pumping, pipeline diameter and source, everything. That's why fluctuations are calculated. What are different types of draft? So the drafts are average daily draft. It's daily how much water is consumed. That is average per capita water demand into population. Maximum daily draft is 180% of average daily consumption. 180% of average daily consumption means average how much is the consumption into 1.8. Maximum hourly draft of maximum day. So this consider this is written as, so for 1.8 times of annual average daily draft into 1.5 times of annual average daily draft. So if you multiply these two things, you will get 2.7 into annual average daily draft. Coincidental draft is, see, if we see the worst scenario, in the worst scenario means maximum, we are talking about, let's say 25th July. This is the hottest example. I'm taking the example. So this is the hottest, assume this is the hottest day of year. So in the hottest day of year, if fire breaks out, if fire breaks out, then the demand would be maximum hourly plus fire demand. But the probability of, this is coincident, the probability of maximum hourly demand on the hottest day of the year, I'm taking hottest day of the year because on that day it will, we can observe maximum hourly demand, and on the same day fire breaks out, so the fire demand, the water will be required for the fire demand also. But this is very rare. This is a very rare. So this coincidence can happen, but it's very rare. So the fire demand is taken as, we can say, like very rare and uneconomical. So we can say, we are assuming here on the hottest day of the year, taking example, the fire will not break, the fire will not happen. So with this day, on this day, the fire will not happen on the maximum. So maximum daily plus fire demand. So some other day the fire will happen. So we'll observe these two things, and maximum will be taken as the coincidental draft. If we design based on this, it will be uneconomical. So on the maximum day, not on the maximum hour, on 25th July, let's say morning 8 to 9, 8 to 9, 8 to 9 a.m. is the highest demand. The fire may break out on 25th July, but not on, and not at this hour when the fire demand will, when there is maximum demand. So it can have, the fire can break out on this day. It can cater the demand of maximum daily, but not for few hours. That's it. So uh, this is the concept here. On maximum day it can cater, but not at the hour when the fire demand is, fire and hourly demand is at peak. So that's why it is not considered, because it will make the design uneconomical. Determine the maximum and coincidental draft for a city with a population of 4 lakh and water demand is 250 LPCD. Let's solve this. Annual, first demand is annual average daily draft. So annual averages, population and average LPCD into 10 to the power 5. So if you solve it, it will come out as 100 into 10 to the power 6 is 100 mLT. Now we need to find maximum daily draft. I'm writing it as MDD, maximum daily draft. So it will be 1.8 times into 100 mLT. So it will be 180 mLT. Now maximum hourly draft. It will be 180. So we can directly solve it as 2.7 into 100 mLT. So it can be written as 2.7 mLT. Or if you want to calculate it per hour on hourly basis, we can calculate it as 270 divided by 24 million liter per hour. So if I solve it, how much will I get? 11.25. Now we'll calculate fire demand. So we can use this formula, Quichelin formula, 3182 under root p. So where population is in thousands and the unit will be liter per minute. 82 under root p. Where population is 4 lakhs. So we'll read in thousand it will be 400. So if you solve it, 3182 under root 20, the fire demand will come out to be that is 14230.3 liter per minute. But we want this for in million liters per day. Writing it as fire demand. So it will come out as 14230.3 and dividing it by 10 to the power 6 to convert it into millions, and then liter per minute. It is liter per minute. So I will divide it by 24 into 60 to convert it into mLT. Let's see how much. Divide by 10 to the power 6 and divide by 60. So it is coming out as we need to multiply it in numerator. The unit is liter per minute. This is liter per minute. It can be solved like -6 uh, milliliter into 24 into how much minutes? 1 day, 60 minutes. And for Q3, 3182 into 20. This is somewhat wrong. If we solve it here, we will get 63640 liter per minute, and then 63640 into 10 to the power -6 into 24 into 60. It will come as 91.64 mld. 91.64 mld. So this is the fire demand. Now we need to find out coincidental draft. The coincidental draft is maximum hourly or maximum daily plus fire demand. So what is maximum hourly? Maximum hourly was 270 mld. 270 mld. And here maximum daily plus fire demand would be, what is maximum daily? Maximum daily was 180 mld plus what is the fire demand? Fire demand is 91.64 mld. So 91.64 plus 180 is 270 is 271.64 mld. So this is the maximum. So let's write it like this. Two 71.64 is out of 270 and 271.64 mld. So this is the coincidental draft. Fine. Which of the following directly leads to increase in urban water demand? Choose the correct option. Which of the following directly leads to increase in urban water demand? So urban water demand. So melting of glaciers has no effect. Population growth will affect the urban water demand. More consumption oriented lifestyle changes. Yes, it will affect. It will increase the water demand. Population reduction. More consumption oriented lifestyle change. Population reduction which leads to increase in urban water demand. So This population reduction means population reduction will not lead to increase in urban water demand. So only Q and R are correct. C is correct here. The correct answer is C. Water demand is mostly water demand is inelastic to water price. Inelastic means if we see here price, and let's write price and demand. Inelastic means there is, if price is changed, the demand will not change. So the graph will come like this. So if even though uh, no, no, it it should be like this. Even though if the price is changing, the demand is not changing. So it is flat. It will be the flat curve. So the price is changing, but the demand is not changing much. So this is called. So this demand is called inelastic demand. So water demand is mostly inelastic in terms of water price. It is inelastic. Which factors contribute as explanatory variable for predicting temporal variation in water demand? Which factor contribute to explanatory variable for predicting temporal variation in water demand? So temporal variation means with respect to time. Temporal means with respect to time. So the built up area will be same with time. Temperature will change with time. Housing typology will be same with time. Wind speed will change with time. So these two are correct. Q and S are correct. So means B is correct. So the correct answer is B. So these built up area and education are exploratory variables for predicting spatial water demand. Whereas temperature and income contributes to explanatory variable for predicting temporal water demand. So this much LPCD is required for institutional and commercial purposes in highly commercialized city. How much? It's 50. It's 50 liter per capita per day or liter per head per day in highly commercialized city. Otherwise, it was 20. Considering breakdowns, considering breakdowns, water treatment plants and pumps are designed for how much times the average consumption. So we studied like maximum daily was 1.8. So for pumps are designed for twice, two times the average water consumption. Considering breakdowns, water treatment plants and pumps are designed for this much times the average consumption. So it's two, like same question. Estimate the fire demand. Estimate the fire demand for a city with population 5 lakhs 500,000. This is the population and average water demand of 250 liter per capita per day using Futuring's formula to calculate the fire demand. So the formula is 3182 under root P, where P is population in thousands. So using Futuring's formula to calculate the fire demand. So 3182 under root P will be in thousands, so it will be this much. So if I calculate it, it will come out as 3182 under root P is how much? P will be 500. 71151 71151.68 71151.68 71151 71151.68. So the answer is C. Correct answer is C. Nal Se Jal. Nal Se Jal scheme is associated with which of the following aspect of water supply? So it is in Hindi it is Nal Se Jal means the water from tap. So it is for provision of clean drinking water, international and interstate water disputes, cleaning Ganga and its uh, cleaning Ganga and its tributaries. So it is Namami Gange program. Provision of piped water supply to every household. That is a different scheme. So provision of clean drinking water is the Nal Se Jal scheme. Sorry, provision of it's a mistake from my side. So Nal Se Jal. So they are saying Nal Se Jal. So from tap. So provision of piped water supply to every household. So this scheme is D. Provision of piped water supply to every household. So it was for with the help of it was to provide piped water supply to every household. A treated wastewater from sewage treatment plant can be used for. So from sewage treatment plant, it can be used for agriculture and horticulture. We know it can be used in for industrial use. It can be used for large scale in construction activity. It can be used if it follows IS 456. So it can be used. So all of these. So the answer is D. If it follows IS 456 or some other building construction codes. Water supply is a state project, and state assigns responsibilities to urban local bodies. ULBR, urban local bodies. So the water supply is a state project. State assigns responsibilities to urban local bodies. So match the government programs with their relevant description. So Amrut is Atal. It is for replacing JNR, and Hriday is heritage cities. Smart cities mission is Swachh Bharat mission is for waste management and sanitation. Smart cities mission is for smart meter and water quality projects. So if I say P is 2, Q is 4, R is heritage cities, S smart cities mission was to provide smart meter and water quality projects. S is 3. 2, 4, 1, 3. 2, 4, 1, 3. So answer is B. This is required to reduce volume of unaccounted water. So what is required to reduce volume of unaccounted water? Metering is required. Metering and unauthorized connections detection and checking is required to reduce volume of unaccounted water. So if you provide the metering and we can check or we can detect the unauthorized connections, we can reduce the volume of unaccounted water. What is non-revenue water? What is non-revenue water? So Non-revenue water is free water supplied through standposts and consumed without payment or lost through leakage. So this is the water which is supplied through standposts or consumed without payments or lost through leakage. So this is the non-revenue water. So this was about today's session. So if you have any doubts, you can ask. So we solved a problem related to the population forecasting, and we went through the key issue related to the water, and then we understood why there is a need to forecast the water demand and how much water is required as per IS 1172. So for stand post, the water to be supplied is 40 liter per head per day. And what does total water demand include? So total water demand includes domestic, industrial, and institutional, uh, for public use, for losses and waste, and fire demand. So the domestic water demand is for all the domestic purpose. Industrial water demand is for the industries like fertilizer, paper, steel, sugar, textile, automobile. And institutional demand includes office, factories, cinema halls, schools, colleges, hospitals, and all. For public uses like for road washing, for public gardens and parks, and if you can see, and we can see public fountains and parks. So all these water required for the public uses. And losses and waste means, and we have pipes uh, to distribute the water. We have pipes, and pipe can't be built very long, so we need to provide joints. So from joints there is always leakage, not always, but most of the time there is leakage, and because of bad plumbing and damaged water meters, because of this loss can happen. And sometimes theft can also happen in authorized connections. So this is because of losses and waste. So now we also studied about fire demand. So to incorporate the water demand due to fire, incorporate the water required for storing in the reservoir in case a fire breaks out. So we have fire demand. So in the reservoir we can see some water should be stored so that uh, when fire breaks out we can supply in emergency situation. So this is the fire demand. And so this now uh, so we understood in the fire hydrant some pressure should be maintained. These are actually most of the time, if you see the fire hydrants in Google, you can see these are red in color, and they are provided in the streets at a distance of 100 to 150 meter. And three pipes can be connected through a fire hydrant. And we need to provide 10 to 15 meter water head so that it can have adequate flow rate, and the water can reach at adequate height, and to overcome the friction loss and to work effectively and efficiently, to so that our fire equipment can work efficiently. So that's why we need water pressure. And we understood like how the water consumption or water demand is affected because of the certain things like living standard. If it is good, our water demand will be high. If the climatic conditions are hot and dry, we can expect more water. But in the cold areas where there is people keeps their tap open because, to avoid freezing, so that and there also we can have more water demand. uh, and based on system of sanitation, like if you have sewerage system like flushing system, you have bathtubs in your home. If the standard of living is good or sanitation is uh, the system of sanitation is uh, good, then we will have much higher water demand. So this is the theory which we understood in this lecture. So now I think we can close this session. Thank you.